when you look at the book, the difference between F7 and F8, most books, like kind of make it seem like you're doing different methods to do these, but it really is the problem that tells you what you're doing here. In the section that we finished before, your inside of your shape always went to the line that you were rotating about. So you had one function, and if you were rotating against the axis, then you were thinking that that shape was full all the way to the axis. So you ended up with the solid shape. In F8, we're going to have two different shapes, two different functions, which is going to give us an outside of our shape and then an inside of our shape so that the inside will be hollowed out. The nice thing about anything geometry is it just works with addition and subtraction. So you find the full volume, like that middle piece isn't cut out, and then you find the volume of the middle piece that is cut out, and you subtract them to see what's left. So, most things in geometry work that way, like when we're working with areas and volumes. If you have something missing, you can just find two separate areas, volumes, and subtract out what's missing. So basically what we're going to have is two different shapes. If you take a cut, a cross section anywhere on the shape, instead of having a disc, which we said was a really thin cylinder, you're going to have what we call a washer, which is a really thin disc with a hole in the center of it. Because you're rotating, they're both going to have the same center, so you'll always have this setup. It really is solving two different copies of the same problem. Find out the shape filled to the middle, find out what the middle would be if it wasn't empty, and take it away. A lot of times when we do this, we use a capital R and a small r, kind of just to figure these out. I'm trying to think what's exactly is supposed to go on these lines here. So the volume of our new shape, our shape with the hole on it, is going to be pi capital R squared minus pi little r squared, which is the same as bringing that pi out and saying r squared minus r squared. Those are just the radiuses. We will replace them with f of x's and things like that. These should always be dx's, where big R is the radius to the outside of the object, and little r is the radius to the inside of the object. Both pieces of that formula come from the area of a cylinder formula, which is pi r squared h. Obviously, the pi is the pi. Obviously, the r is the r in r squared. And then the little dx, that thickness, is what's taking care of the height in our formula. All right, let's do an example. Or let's look at a picture again. I guess I just liked this picture when I added it here. I don't know if it really adds anything. I think hopefully you were visualizing most of what was going on from the picture above. All right. Let's do an example, and let's just start out rotating about the y-axis, because that's what's there. So we're rotating about the y-axis. That means we need our functions in terms of x's, which they are given to us here. So we have two curves. We've got the line y equals 2x. We've got the line y equals x squared, and we are rotating about the y-axis. That gives us the bowl shape that you see in 3D on the right. Remember, when we're talking in terms of y, the upper function is the function that's further to the right, and the lower function is the function that is further to the left, or closer to the axis that you're rotating about. So basically just using what we saw there, in this case, our capital R, we're going to be in terms of y, so we'll call that the blue, which is the square root of y. And our little r is y over 2, the line. And the picture has both of our functions solved for x equals. When you're integrating, always look at the d at the end. Since we're going around the y-axis, we're going to have a dy. That means we should have y values as our integral limits. So we're going from 0 to what? 4. Yep. pi r squared h. So it's going to be capital R squared. So the square root of y squared minus y over 2 squared. Pi r squared h. Got it. Could make that as two separate integrals, but it's just a little bit simpler to put them together like that. So we've got pi integral from 0 to 4 of y minus y squared over 4 dy pi y squared over 2 minus y cubed over 12 evaluated from 0 to 4. So we end up with 16 halves minus, I'm only going to multiply 4 twice because I'm going to divide it out in that denominator of a 12. So instead of doing 4 times 4 times 4 and then dividing it by 12, I'm going to get rid of one of those 4s and give myself a denominator of 3. And then I only have 16 there. Yeah, how about a pi out in front? That would help. Boom. Thank you. I know the answer. I'm just going to bring the 16s out front and make it 16 pi 1/2 minus 1/3 to make life easier with the fractions, which is 16 pi 3/6 minus 2/6. So finally, 16 pi times 1/6 is 16 pi over 6. Last but not least, 8 pi over 3. Yeah, and lots of them are just set up the integral. Lots of them are just, calculator active. So not too many tedious calculations. That one wasn't awful. But factoring that 16 out made life a little bit simpler there. I would have had to have multiplied 16 by 3 and 2. Questions on that? All right, let's do the same thing, but is that the same thing? No, it's not the same thing. Find the volume of the region enclosed by y equals square root of x and y equals x squared is rotated around the x-axis. So we've seen these two functions together before. These are the two functions from cross sections. So we have the square root of x, we have x squared, and they meet at 0, 0, and 1, 1. Because we're squaring separate in this formula, if you don't identify the upper function correctly, you'll get a negative answer. So we do need to identify the upper function correctly. That's easy. It is the square root of x. But this is just going to be the integral from 0 to 1 of pi on the outside, square root of x squared minus x squared dx. That's not too bad. X squared over 2 minus x to the 5th over 5 from 0 to 1. Got 5/10 minus 2/10, so it sounds like 3 pi over 10. They're either, I don't want to call that easy. They're either just simple like that or so, unwieldy that you've got to use a calculator to do them. And then last but not least, this really is only just a 3 example packet because really it's just a matter of practicing them and getting them down. what happens when you go around another line. This is the exact same thing that happened when we went around a line that wasn't an axis in F7. It's just that we have to do it twice. Basically, you can kind of see that big R. I'll show it here. Big R is this orange line here. And that big R is your axis line, which is 2. And our function value, which is y over 2. So this is y over 2. So our big R is 2 minus y over 2. And little r would work the same way. We would just use the other function. It would be 2 minus square root of y. These things are going to get squared, so whether you use 2 minus y over 2 or flip it around to y over 2 minus 2, they are both the same thing once they're squared. So the order doesn't actually matter. That's why we just get to use the formula. So we'll go ahead and write our integral. We are rotating about a vertical line, which is x equals 2. We have to picture, like, this is the one thing where the association isn't direct. It's a vertical line, so I have an x equals. That's the same as the y-axis, same direction as the y-axis. So I have to think, okay, I need a dy there, which means I'm going to use y values. So dy at the end, I'm going to integrate. This is the same two functions from example 1. I'm just going around a different line. So I'll still integrate from 0 to 4. And it's going to have a pi on the outside. 2 minus y over 2 squared minus 2 minus square root of y, but squared. And that is an integral for a calculator. Because you'd have to FOIL 2 separate things out, 6 different antiderivatives, possibly a couple that are maybe a like term in there somewhere. So type away. If I had one hand, yeah, I would. There it is. Battery's low. Second pi alpha function integration from 0 to 4. 2 minus what's squared minus the quantity 2 minus second square root of x but squared dx. I did mine in terms. It does, yeah, if you're typing in, I'm doing it in the calculator, so it's just easier to type x's. That's what I got too, 8.378. Yep. I think one advantage to do it, well, I don't know. It's kind of annoying to type in the calculator. As I was typing it in, I'm like, I should have just used Desmos. But either way, we got the right answer. Having those combined parentheses, I feel like, is a pain in the neck in the calculator. But if that's our biggest problem, we're in good shape. All right.